I am going to talk about gasoline and more, and why we must replace fire in our energy system. And I'm going to give excerpts of a much longer presentation, and hopefully I'll be able to say what I need to say in my 15 minutes here. So another possible title for this is Firing Fire, Why We Need to Cool Down the Energy System. And I'm going to start us off with a question about this block of graphite. And graphite is pure carbon. It's the main ingredient in pencil lead. On the slide there, I've got it with a quarter so you can see that it's 2 by 2 by 6 inches. And I want you to think about how it compares to the amount of carbon in a gallon of gasoline. Is it a lot less, about the same, a lot more? And if I wasn't in such a hurry, I'd do a show of hands on that, but I'm going to cut that out for the moment. This is also, there are many sort of descendant talks that are all kind of interrelated. This is also, some of this is also part of the talk, Fear is Our Best Hope, Moving from Climate Anxiety to Climate Action. And oops, that one I did want to go on. Want to show of hands, is there a climate emergency? So actually I can't see the participants, so we'll just imagine that most of you think that there is a climate emergency. I'm guessing that is the case. Another show of hands, are you now, or have you ever been scared about climate change? And again, I'm guessing most of the hands go up. And a third question, third and final for this set here, is should we be honest about our climate education and communication efforts? And again, I'm guessing most of you raised your hands. My goals for today are to astonish you, scare you, not leave you scared though, but give you courage and motivate you to act, and give you some tools for upping your climate teaching and action game. And now, as I said, I'm going to skip ahead to the word of the day. The word of the day is fire. In the longer version of this slideshow, I interspersed the white slides with black text, with white text, which is strategy slides. And I'll share this presentation before we're done today. We're going to jump ahead again, so skip most of the strategy slides to talk about one kind of carbon dioxide source, and that's gasoline. So we're going to think a bit about a gallon of gasoline. Americans burn 376 million gallons of gasoline on the average day. That data is from 2023. That's more than a gallon per person per day, which should make you say, wow. And I'm going to throw around some big numbers. And so I want to take a brief interruption to talk about scale. There's zero, there's a trillion. If we were in person, I'd have folks come up and I would put zero on a Post-it note on one corner of the front wall of the room, and a trillion on the opposite corner of the front wall, and have everybody come up with Post-it notes with a billion on it and put it where they think it goes. Since we're virtual, I'll have you do that online there, and hopefully very, very speedily. So if you can take a moment and do that. And for the sake of time, I'm actually just going to fly by it, but do that, and we'll come back and look at your responses perhaps in a moment. So there's zero, there's a trillion, and the correct answer is that everything goes in the first 1/1000th of that length of the line. The commonly named numbers that we talk about pretty regularly, 1,000, a billion, trillion, I skipped them, 1,000, a million, a billion, and a trillion. Each one of those is 1,000 times larger than the one before it. And we don't generally get that very well. So this is responses to that from an earlier online session. Very typical responses there, spread largely across the first 2/3 of the line. And that, of course, is not right. And not understanding that has some consequences for us to think about a lot of issues with climate and energy. And I honestly think that if more people understood scale, the world would be a much better place. It's hard to understand scale. Some strategies for working on that I'll share quickly. And thinking about this is something that everybody is familiar with. And 1,000 seconds is about 17 minutes. 1,000 times 1,000 again is 1,000,000, and 1,000,000 seconds is about 12 days. So when you go from 1,000 to 1,000,000, that's the change we're talking about. And 1,000 times 1,000,000 seconds brings us up to 32 years. So there are some people on this call who are probably about 500 million seconds old. Since we've got some students on here, I am coming up on 2 billion seconds old. And 1,000,000,000,000 seconds is about 32,000 years. And that goes back to before the dawn of civilization and agriculture by most considerations. And Homo sapiens, us as a species, have been around for less than 10 trillion seconds, less than 320,000 years. I think the best guess right now is about 300,000 years for the dawn of Homo sapiens. And that's an example of social math, which I'm not going to linger on, but it's a way of helping people understand big and small numbers. So back to gasoline now. We burn, again, about 376 million gallons a day. And we want to think about where it goes. And a gallon of gas weighs a little over 6 pounds. So you can maybe picture holding a 3/4 gallon or a gallon of water that's 3/4 full, because water has a density about 3/4 that, or gasoline rather, has a density of 3/4 that of water. So if you fill up a jug 3/4 full, that'll give you a proxy for thinking about that gasoline. And if you use 10 gallons a week, where does that 60 pounds go? Well, in order to figure that out, we need to know a bunch of things. First off, we need to know that matter can neither be created nor destroyed, only changed in form. And in order to figure out what's going on with it, of course, we need to know what gasoline is. It's a complex mixture of hydrocarbons. And on average, its chemical formula is C8H18. And if we had more time, I'd prod you to give me a name for that chemical. It's octane. And what do you get when you burn octane? Well, you get carbon dioxide and water. And we're going to look at that in cartoon form. And I'll also note that I made this presentation using Apple Keynote because I like their animations better than PowerPoints. And now we're gonna run that combustion reaction in a moment here. There are our oxygen molecules. There's our octane molecule, and we're gonna give it a spark, and it combines. So we end up with going from 1 octane molecule and 12.5 O2 molecules to 8 carbon dioxide molecules and 9 water molecules. And when we look at those carbon dioxide molecules, and there are the water molecules, but when we look at those 8 carbon dioxide molecules and compare it to the octane molecule we started with, we can see that the CO2 weighs a lot more than the octane that we started with. That's not magic, it's chemistry. So it's pulling oxygen from the air. It's not just the gasoline to produce the carbon dioxide. So what that means is when you burn this 6-pound gallon of gasoline, you end up producing 19 pounds of CO2. And we do that in the US 376 million times a day as of 2023. And that's an example of the power of surprise. And I'm guessing most of you were surprised by that. And as educators, we should think about how to use surprise strategically. And again, if we had more time, I'd ask you for examples of where you've learned things by surprise and where you've taught by surprise. And again, I'll share the slides so you can get to that. So now we're going to think about that 19 pounds of CO2. So a gallon of gas is pretty easy to picture and doesn't seem weird to think that it weighs 6 pounds, but 19 pounds of an invisible gas is a bit harder to understand. So we're going to think about gallon-sized balloons and how many gallon-sized balloons it would take 19 pounds of CO2. So I've got a balloon here, and if we were in person, I would hand some out and ask you to hold it empty and think about how much it weighs, and then fill it up to about a gallon size. Normally I have a gallon jug and I forgot to fill it out for this morning or this afternoon. But that's about the size of a gallon milk jug. So how many of these do you think it would take to hold 19 pounds of carbon dioxide? And of course, you got to subtract the weight of the balloon itself and just think about the contents of the balloon. So does anybody want to put in the chat some guesses on how many balloons it would take to hold 19 pounds of CO2? And, a sort of helpful thing along the way is to think about some other things that weigh about 19 pounds. And again, for the sake of time, I'll just rattle that off. Might be a 1-year-old child, might be a really large cat, like the larger of my 2 cats. A 20-pound bag of anything is in the ballpark. So how many balloons, gallon-sized balloons, would it take to hold 19 pounds? And we'll just spill the beans. It's about 1,100. That's a lot. And if we had 25 people here, everybody would have to blow up 44, since I think we're about twice that. Everybody would have to blow up something like 20 balloons in order for us to get enough balloons to hold the carbon dioxide from burning 1 gallon of gas. So we'll look at that in animation form again. There goes 100 balloons. There's 200, 300, 400, 500, 600, 700, 800, 900, 1,000, and 1,100. That's a lot of balloons from 1 gallon of gas. You could also do the calculations to figure out how many balloons worth of oxygen it took to do that. And so burning that 19 pounds of gas produces 6-pound gallon of gas yields 19 pounds of CO2. And while we're burning, I forgot to update that. Last year, in 2022, we only burned 369 million. So we went up last year. There was a big dip in the pandemic, but we are now burning over 7 billion, or producing over 7 billion pounds of carbon dioxide every day just from burning gasoline, which is about a quarter of US emissions. Now we'll jump ahead back to our graphite. And I'll ask again, is it a lot less, about the same, or a lot more? And I'll spill the beans again as we take a look at it. A gallon of gasoline is about 87% carbon by weight, which if you think about that octane, you can maybe picture that a little bit. That means there's about 5.5 pounds of carbon in every 6-pound gallon of gas. And pure graphite like this is pure carbon. And that's not enough. I think this is enough. And I will say, no, we've actually got to go to this. And this is how much carbon is in every gallon of gasoline that we burn. It, of course, doesn't look like this because it's in carbon dioxide, which is an invisible gas. But that much carbon is coming out of your tailpipe for every gallon you burn. And I will confess that I meant to order a 6x6 by 2-inch block initially, and I goofed on the form and ended up ordering one that's a third of the amount. And that actually, I think, ends up working well pedagogically, because the real answer is just too unbelievable. So working up to it is a step in the right direction. And I'm going to go on to the next piece here of talking about how we might take that carbon back out of the air. Of course, it's very important to recognize that the simplest thing to do is not break something rather than break it and then fix it. And we didn't exactly break the atmosphere, but we changed the way it works. And now we want to figure out how to change it back to the way it was when I was born, maybe, and take that carbon back out of the air. And the simplest technology for doing that is planning stuff. Wood, it turns out, is about half carbon by weight. So if you want to take 5.5 pounds of carbon out of the air by growing wood, how much wood do you need? Well, we'll make the math easier and say that wood is 50% carbon, which means that you need to grow 11 pounds of wood to sequester each gallon of gasoline we burn. And we can't let that wood burn or decay because that'll put the carbon back into the atmosphere. And that should make you say, wow. And it just so happens that an 8-foot 2x4, standard 8-foot 2x4, like this one right here, weighs about 11 pounds. So for every gallon of gas, you need to grow this much wood if that's your solution for taking the carbon back out of the air. And we're not doing that. And we can go on from there. There's me and my 2x4. And that means 11 pounds times 376 million is over 4 billion or 4 billion pounds of wood every day, 1.5 trillion pounds a year. And that should make you say, wow. And I'm going to stop here with wherever we replace a hot process with a cooler one, we reduce emissions. And that's where I think the hope and the courage can come in, is figuring out how we can replace fire in the energy system with other ways of achieving our goals. And I'll note that methane, which is the largest source of energy in the United States right now, I believe, things are rapidly changing. But methane typically burns at about 3,500 degrees Fahrenheit. And for most of the things we do with it, we do not need that level of heat. And it's exciting to think about other ways to do the things that we do. And I will stop there. I don't know how I did on time, but I'm going to stop there.
Thank you, Don. You were pretty much pitch perfect. We have
awesome.
we have about 2 or 3 minutes for questions.
Great.
I think that was a very good perspective on, especially connecting to well, many audiences, but especially younger audiences, this problem of scale and how much of a vicious problem it is in our system. And while we're waiting, oh, go ahead.
Well, I'll just note, I think we miss communicating the urgency of climate change an awful lot of the time. And understanding scale, helping people understand scale, I think is really fundamental to helping understand the urgency of the situation.
Now, we do have one question in the Q&A. So you were mentioning growing wood as a way to help offset it. And they were wondering other types of life, in this case, like native grasses that may support wildlife. Do you have perspective on those kind of other things that we could look at as well?
Yeah, I mean, generally, plant matter is about 45 to 50% carbon. So that all sort of works towards the same end. Grasses may have a lot of their root system underground, so some of that mass may be protected from wildfire. And thinking about fire and wildfire is very important. And I recommend the writings of Stephen Pyne, Pyne, who is a fire scientist. And the managed fire of grasses is an important part of making the ecosystem work. So there's a lot of really rich areas where you can go with that. And invasive grasses, like cheatgrass in Colorado, can produce more problems with wildfire than native grasses. So there's a lot of interesting ways to go with that. And I see Jennifer's got a hand up.
Yep.
Just a quick question, Don, can you talk about how long wood can last in the ecosystem and store carbon as opposed to a grass? What is the sort of time cycle difference?
There's a great question that I do not know the answer off the top of my head, but it may well be in our just a moment. Our grasses, we have a really rich online text called Earth at Home, and the grasses section may include info on that. I have not read every page of it. I wrote some pages of it, but I'm trying
share
to get
that
back to Zoom. Where'd
resource
you go?
in the chat?
But you may find info here.
Awesome.
There
Thank
it
you
is.
for sharing that.
And I'll also put the Earth at Home climate page, where you can find a lot of more climate specific materials. And I'll before the hour is up, I'll add a link to the presentation.
Thank you.
This has been a production of Cornell University, on the web at cornell.edu.